I am muted. Can you hear me? Okay, thanks. Yeah, so let's be plus trees. And when you want to run workloads on any data structure in practice, including data plus trees, there are two main classes of workload. They're called OLAP and OLTP. And OLAP is online analytical processing, and OLTP is online transaction processing. And these are the two main use cases that you can classify a lot of different workloads into. And traditionally, OLTP and OLAP there are two different types of systems. You don't run the same, usually you don't run the same, or like in history, you don't run the same workloads on one system, like you would do transaction processing, like online updates, for example, on OLTP databases. And at some point you would like dump everything and convert it into an OLAP data warehouse, but also called like data lakes. Yeah, and the difference is that OLAP is optimized for data analysis and reporting. So like the workloads look very different. You often like scan through a large port of the data, and OLTP is optimized for transactional processing. Like there's transactional updates or real-time updates. Yeah, so like if you have some stream of data, you want to accommodate it into your data structure. And traditionally, systems, like in practice, are optimized for one or the other. But recently, there's been some exploration into combining both functionalities into one system, probably because this dump and conversion is expensive, but also because often you may want to run both types of workloads at the same time. But usually, like you can run both workloads on one or the other, but usually they're not optimized for like the other one. So they may do it really slowly. Yes, sorry.
Can you give an example of what an online transaction processing system is?
Like,
what an OLTP, like what are the operations that you do?
Oh, yeah, just like regular database operations like insert, find, mostly insert and find. I guess in database language, it may be also called put and get. In YCSB, as you probably know, YCSB is an OLTP generator. So they generate you insert find, and they also generate you range scan, but the default YCSB generates you range scan of length 50, average length 50. So it's pretty short.
Like superset of OLTP output?
They are separate. I guess OLP you can also, it may be separate because I'll talk about it later, but the scan in YCSB requires you to do it in order, whereas the scan in OLP may not be in order. So like they have intersection, but they have intersection in their API, but the intersection in their actual workload is not that high because like, even if OLTP does scans, they're usually super short, whereas OLAP may be doing like large analytical processing through the entire thing. Like usually you generate like summary statistics, for example, something like that. Make sense? Yeah, I'll talk about it later, but YCSB is a popular benchmarking generator, and YCSB generates OLTP workloads. Okay. In B-trees, like there's this theoretical notion of what we should set B to, but in practice, you actually have to choose a block size for your node. And this is like a user set parameter, and it can be whatever you want. Easiest is to set it to like a power of 2, because if you set it in bytes, your elements are usually in powers of 2. And unfortunately, depending on the node size, B-trees exhibit this trade-off between OLAP and OLTP performance. So this plot, the x-axis is node size in bytes, and the y-axis is normalized performance, and one is like the best performance as a function of node size. And so there'd be like one point at which any of these node sizes achieve 1, which is the best performance. And you can see that insert and find are dropping off as you increase the node size, and range query is going up as you increase the node size. And ideally, if your data structure supports both of these operations, you want both of these things to be good. But as we've been showing, like you have to choose one node size, or you can choose 2, but it actually only matters that you set the leaves to, because the leaves account for most of your operations. So you can choose like one node size for your leaves, and you basically are somewhere along the trade-off curve. And basically you have to pick whether you want to be good in range query or point. And I want to emphasize that this is like a practical thing. In theory, if you set your block size equal to theta z, all the bounds are fine. But this is like a practical like performance thing. Yeah, and like I said, the reason that we care about long range queries is because they're important in real-time analytics and graph processing. They're often used to scan through the vertices, which is like these primitives that we often use in graph algorithms. So you can see from this trade-off, large nodes speed up the range scans at the cost of point inserts. And we want to design something that is good for both. So in YCSB, I think they're called put and get in YCSB, but I'll call them insert and find, because that's like more traditional data structure language. You have these point operations, insert, you have a key of value, and you want to insert this into your data structure. And you have find, and you give it a key, and you return this is like a traditional find, like you return a pointer to the smallest thing larger than the key that you're looking for. If K is in there, you would return the pointer to K, but if it's not, then you return the thing right after it. In a B tree, the way you would do this find is here, there's only two levels in your B tree. You start at the root, you look at the pivot that encompasses this 15, and then you follow it down to the start leaf. And here we don't find 15, but then we return 16. So that is how you define the B tree. And find, we talked about this last time, but I just wanted to recap it, is find is like a key sub operation in your insert, because the way that insert works in B trees is you do a find the correct location, and then you put it in the array, and you may have to do some splitting if you are full. So for example, here we're saying 8, and you do the same find, you find through this thing, and you don't have any space here. So you have to promote one of the elements and split this leaf. So this leaf gets split into half, and arbitrarily I put like it's uneven, so one of them has to be bigger. I put 5 in the second half. And now the head of this leaf needs to get promoted up one pivot. So 5 gets promoted as a pivot, and now every leaf has some pointer from the top. One node up. So actually, like you have B pivots and B plus 1 pointers, but that's like good. You have order B elements in every node. Yeah. Does this, like, people remember how to do this? All right, so yeah, that's how you do B plus trees, and B trees are similar. And like I said, there's 2 kinds of range operations, and it depends on the use case, which one you might care about. So in the YCSB, they give you this API to do range iteration in sorted order. To simulate, like they give this example of simulating threaded conversations, like for example, like I want to load some messages on this date, or like from this user or something. And so they give you this API, iterate range, which takes in a start key, this length, and some function that you want to apply to all of them. Like the function could just be like print or return or something. And length is the number of elements that you're going to return after the smallest key. So this is like, it requires you to return them in sorted order, and it gives you like how many elements you're going to return after that. And the default length in YCSB is like 50. I think on average is 50. Actually, like in their benchmarking, it's like a uniform random distribution between 0 and 100, but the average is 50, and most of them are small. I think 100 is usually pretty small in this context. Okay, but like I said, there's a second. This is the second type of range operations. In some applications, you might not need access to the elements in order. In B trees, everything is in order anyway, so like how you would implement these is the same in both, but the API is just slightly different here. Instead, you get the start and end keys. This is like another way that you can express range operations. You just like, give me all the elements between 100 and 200, for example, in any order. And you can just return a set. And yeah, you get start and end key, and you apply some function. Again, this is the same as the iteration. And one key use case that you might use this in is graphs. So like some key operation that you do in graph algorithms is iterate through all of the neighbors of some vertex in any order and apply some function to them. So how would you implement these in B plus trees? Using this iterate API, for example, return me the 5 elements in sorted order starting at key 15. And this is just the B tree that we had earlier. It's based on find again. You get this pointer to the smallest key at least 15, so it would be here. And then you would just do this you get an iterator, and then you just step forward 5 times. So like here, you would get 16, and then you would just call the iterator 5 times until you got to the end here, 23. And then you would stop. And in B trees, you can use this. Once you get the iterator, you can use the exact same method for the other range API, but you just modify the end condition rather than stepping forward some number of times. You step forward until you see something bigger than your end, or you got to the end. Like I was saying, there's not one best node size for all the operations, like there's the trade-off between point and range operations. Large node sizes can increase your range query throughput, but then your inserts become slower. And this is just another way of visualizing the same data that I heard earlier, but this is not normalized anymore. So the way that you read this is range query throughput. Up is good. This is like operations per second. This is insert throughput. Right is good. Right is higher. You want more inserts per second. And these are like different settings of your node size. So this setting is the best for range queries. This is the biggest one, 2 to the 16, but it's 2.4x faster than the lowest setting for range queries. Or sorry, not the lowest. I guess better than the optimal for point queries, but it's 16x slower for inserts for the best case for point queries. And on this side, 2 to the 10 is its best case for point inserts, which is using 1 to the 15. And I guess down here is just worth it every way. So you want to consider those, but past 2 to 10, you're Olympus Pareto optimal curve, but you're either better in inserts or you're better in range queries compared to some other settings. So you can do this distribution point, and you can find that you can, like, as long as you're on this line, you're trading one for the other, and you're not necessarily worse in both axes. Okay, so in this work, we're trying to answer this question: how can we achieve good performance on all of these operations? We want to maintain good point insert performance, like over here, but we don't want to pay for it in range queries. And yeah, just to explain the reason about this trade-off, increasing the size of nodes decreases the number of nodes accessed during long range queries. So previously I was showing you, like, you do this iteration through the nodes, and if you have small nodes, suppose that you're iterating through all these blue squares, you have to do a cache miss here to get to the next one. And if you're reading over many of these nodes, then you have to do a cache miss on each one. And on the other hand, if your nodes are huge, you're iterating through the same number of blue squares, but all of these axes are now contiguous. However, if you make the nodes larger, because the internal, we don't really think about it that much, but like when you think about what you store the elements in a B tree, like they are sorted arrays in every node. So when you insert something into your array, you have to shift everything else down to maintain the sorted order. And so you just put it in and then you shift stuff down. And in larger nodes, you just have to shift more stuff down on average. So ideally, like I said, we want to improve performance to overcome this trade-off. We want to be somewhere up here. Yes, sorry.
You said you have to do more shifts for the larger ones, but then the number of shifts would just be the number of nodes to take, number of values which are greater than the value that is inserted.
The number of things shifted is greater, yeah, than the number, or the number of things shifted is the things that are greater than what you inserted.
No, like as in like in the first case, the total number of values is lesser, so you have lesser shifts. But in a larger node, you just have more number of values. That's why you're shifting more.
Yes, exactly.
But then if it's already full, if all the nodes are full, then both of them will be the same.
If they're full, yes, because you just copy everything.
But then like most of the time you'll make sure that you're loading the values at the time. So the insert would really not, like, it'll be the same performance for both large ones and small ones.
What do you mean loading B at a time? Like most of the time you only do a split 1 in every B insertions in the leaf level, and higher up you do a split, like it's 1 in every B, 1 level up, 1 in every like B squared, 1 level up from there.
Like, but like, so this would work if like on average there's a lot of empty spaces in each node.
Like the fact that you can shift requires you to have at least 1 empty space in the node.
So,
You see what I'm saying? Like, yeah, so you're only allowed to shift if you have at least 1 empty space in the node. But if you do have to shift, which happens every time you do a promotion, modulo splitting, just like the magnitude of stuff that you have to shift is proportional on average, it's like half the number of half the size of the node. And if your node is bigger, then you have to shift more stuff. Make sense? Thanks. So could you make like a B tree with like a linked list inside the node? You think? Like right now you can think of a B tree like this basically. Like these are your nodes. Like this is your B tree, you have some array, and then you have like this implicit node structure. These are connected by pointers. So you're saying like you want to make this like instead like this. You can. You can. And then like if you want to insert, you can make it like this, something like that. Yes, you can. But then now to do a scan, you have to read over, you have to do n random access proportional to this list length. Yeah. So yeah, it's a good question actually. And actually I want to kind of get at this, like, this is like the intuition behind what I'm going to tell you later, which is like, this thing does not have to be a sorted array. It can be whatever you want. Like it can be a linked list, it can be a hash table. These like this higher level structure and this internal structure are totally separate. And like, depending on what is in here, then they have the trade-offs of whatever is in here. But also, the trade-offs are a little different than you might think of traditional data structures, because like, even when we talk about these things being large, they're still on the order of like, at most like kilobytes. So when you talk about scaling data structures, like usually you think of scaling them to like millions or billions. But like things that are asymptotically better as you grow to n are not necessarily better when you limit them to like kilobyte size. Yeah, good question. Yeah. Questions? Anything else? All right, so yeah, so going back to the high level goal, which is we see this issue and we want to be here. And spoiler alert, we were working on something that indeed brings you here. And again, this thing is called BP tree, and you can also play with the node size settings and do this curve drawing. And some of the configurations are up here in the range that we want to be in. And it turns out that the best one was about 2 to the 14 size, which is way bigger than 2 to the 10. And the insert is very similar speed compared to the best case point insert for B trees, whereas the range query is about 1.5 times better. And the way that you do this is exactly not by switching it out for linked list, but by switching it out for something else. Yeah, so I'll tell you how it works. Like I said earlier, leaf nodes are the hotspot in B tree variants. The way to think about this is that 1 in every B inserts is going to get promoted. And if B is usually on the order of like at least 10, maybe even 100. So almost all the elements are only in the bottom level. And like if B is 10, which is like a very small estimate, then like 10% of the elements would be in here. That's a very small fraction of the insertions. And so what we came up with is you replace this sorted array with something like a buffered array. And one way to think about the structure is that rather than having like one sorted array, it's kind of like collapsing 2 levels of the tree into one giant contiguous array. And then you need to do some maintenance to make it work. The first is this header, which tells you basically like each of these things you can think of as one of the arrays in the initial B tree. And then this thing is it's like the pivots kind of, but it's now concatenated to the front. And then there's this buffer in front. The buffer just takes some ideas from write optimization. So buffer is just like, it amortizes your writes. You don't have to keep shifting everything down every time. You can create some space in front to buffer it, and then later on you flush it, just like regular buffer data structures. Yeah, and the reason for this header, it's very similar to the pivots. It just bypasses full searches in your array. You can like these tell you like the range of elements in every one of these blocks. So here, 7 and 15, all the elements in this range would be between 7 and 15. Here, everything is between 15 and 19, 19 and 89, and then everything greater than 89 up to the next node, or infinity if there is nothing after this. Yeah. So this is this is one contiguous array. And you can imagine, you just malloc the space and you manage it. It's just memory. And you can replace, we just replace the leaves because like I said, the leaves are the hotspot. You could put this in any internal node, but it's just easier to do the management if it's just in the leaves. And kind of like when you think about it at an API level, like your internal data structure, it only needs to support some base operations like insert, find, range. And as long as you implement those on top of anything, you can put it in here. Okay, so yeah, so I can explain how to do the insertions. This is the same example as we just had. Suppose that we wanted to insert this number 22 into this array. First, we use this buffer. And because the buffer happens to have space, you just put it in there. And then you don't need to do any shifting, and then you call it done. And now it appears in your data structure. And notice that this thing is not sorted, and these are also not necessarily sorted. So this is different than your regular B-tree structure. And like other buffer data structures, you may have two copies of every element in your nodes. You can have one copy in this buffer and one copy like in the more like stable part down below. And then we want to insert another element because we're trying to insert this 27. We put it in here and now it's full. So we need to clear space in this front area. So the way this works is that you look at your log, which is this buffer, you sort it, and then you use this partition. You use these partitions to tell how many things from here are going to go in each of these segments. So here, 8 is a repetition. So there are already 2 elements, and there are 0 new elements going to it because 8 is already there, and it just needs to get overwritten. There's nothing going into this second one because there's nothing between 15 and 19 in this buffer. 3 elements are going into this third segment, and that's too many, but 0 elements are going to this segment. So we did something super naive. If any one of these becomes full, just like rewrite the entire thing evenly. Yeah, and because at least one of them became full, it's really easy. You concatenate all the elements, you sort them, and then you distribute them equally across the blocks. Yeah, and that's how you do insertions. So this redistribution scheme is similar to earlier. I think I talked really briefly about packed memory arrays, and this is similar to the redistribution scheme in packed memory arrays, but it's way less complicated because packed memory arrays, you need to maintain the tree structure. And the way that you do the redistribution in that, you look at your neighbors and you only redistribute part of the array potentially. But here, because the thing is of bounded size, probably up to about 1K or 10K, you can afford to just like rewrite the entire thing every time. But this thing will not work as in, well, like it will be correct, but like it probably won't be fast as n goes to infinity. But you can, like, the point is that you want to leverage the fact that this thing is often small-ish compared to n. Yeah, so like I said, another main operation that you want to do is range queries. We have this API iterate range. We start from this key 7, and then we want to iterate 2 things. And you can see that range is going to become way more complicated in this, not that much more complicated, but more complicated in this compared to just like a regular array. Because in a regular array, you just find the start and walk forward. But here you need to, basically you need to keep 2 pointers, one in this buffer and one in this, this part is called the header, this part is called the blocks. So you need to keep 1 pointer in the log and 1 pointer in the blocks, and you just basically do like a 2-finger stepping. And you may need to sort as you go. The header is already sorted, but this log is not initially sorted, and the blocks are also not necessarily initially sorted. So this thing is now different because previously range queries are read-only, but now they may become not read-only. And then you just advance the pointers as you need to perform your iteration. We started at 7, you walk forward, and then you walk to your block. And you can see here, there's 2 copies of 8, but because of the way buffering works, the newest one is always in the buffer. So you ignore the later one. Yeah. So you take this one, you take this one, you ignore this one, and that's the end of your iteration because we only ask for 2 things. There's another small optimization, which is you might imagine that the sorting becomes a bit costly. Like definitely this thing adds computational overhead to range queries. To avoid some of the computational overhead, we also keep this bit vector, which has length num blocks. And the bit vector just tells you whether or not the elements in every block are sorted. So there's one bit corresponding to each block. And 0 means it's not sorted, and 1 means that it is sorted. And you can maintain this thing not online after every insert necessarily, but the inserts happen in the log. You maintain this thing when you do flushes into the rest of the data structure. So it kind of amortizes the cost of having to do the sorts as well. Yeah, so you can maintain that during flushes in your inserts, and you can also maintain it in your range queries, because your range query may have to sort things online, but you can just set the bit if you did, to avoid you having to go back and sort it later. Questions?
So like you're optimizing for like, I guess the sorting overhead would be high here, right? For example, you have to sort the log buffer space whenever you're doing the range query, and then like again, when you go into the particular block, you go into a linear scanning.
Mhm.
So in the overhead for the range query is very high. So like the upper bound on as to how much you can get on the range query would be limited.
Yes, exactly. Like I'll show you more numbers later, but like if you have the same size array and the same size of BPA, range query in BPA is slower for sure. But you're not comparing the same size nodes. You're comparing like a large BPA compared to a small array. Because you want to, like, you're keeping the insert performance constant. And given that you want to improve the range performance, like if you could just naively increase the node size, you would pay for it in terms of insert performance. Does that make sense? Yeah, exactly. So there, it is true, like there is this computational overhead to maintaining the structure, especially for range queries. But the whole point of this complicated thing is like, you want to make up the insert cost pretty much of increasing your node size while maintaining some of the range query performance.
And also like you insert operation, you say you if there is like an overfill, you just do the portion and isn't that like expensive compared to?
Yes. Well, it's not so much worse than shifting, because on average, every time you insert into a B tree node, on average, every time you insert into a B tree node, you have to shift half the stuff.
But then you do it only one by each times.
Yes, but this like redistribution is also only like 1 by however big this thing is, which is some user set parameter at worst. Yes. Yes, yeah. So if the log is of size B, you only have to flush it every B insertions. And as you said, like the worst case is if they always go into the same block. But still, you would have to rewrite the entire thing over every B insertions. But maybe that's still less writing than the naive case, because like you would have to write like B times size of this over 2 in a B tree.
That would be the same even in B.
Yeah, like it's not,
It's not
in the worst case, it's not worse than a B tree. And in the best case it's uniform random. And in the best case, you have to rewrite the entire thing, one in every N, where N is this entire thing insertions. Because like everything is evenly spread, and like they would all get full at the same time. In some sense.
I think
Yes, yeah, exactly. Because in a B plus tree, yeah, you are doing B squared shifts for B insertions, but because it's usually in IO models, B is like a constant. well, B is like a parameter of the model. And in the IO models, you fetch B elements with unit cost. And so like you can shift them for free. But of course, like in practice, it is not for free. Yeah. We'll talk more about models later, but that's basically the idea. Good. Yeah, so we can talk about concurrency control. I didn't talk about it at all. Like this entire thing has been, this is like in the nodes, and concurrency control is like one level up, like in the node level. Like we're here, and then we want to go like here. We talked about reader-writer concurrency a while ago. Recap. There's regular locks. Regular locks are just like a bit set or not. There's more complicated locks. A popular one is called reader-writer lock. And reader-writer locks have two modes. They have read mode or write mode, and they allow you to have concurrent access for read-only operations. So unlike a regular lock where nobody can take it, no matter what the operation is, here you can take it if you can have arbitrarily many readers, but only one writer at a time. And nobody can read while there's writing because of course, like the data may become invalid. So, and the way you implement that is you have one writer flag and you have a reader counter where the number of counters you have is equal to the number of threads. And to take it, you check if the writer flag is set. Sorry, if you want to take it in read mode, you check if the writer flag is set. And if it's not, then you can take it in read mode. If you want to take it in write mode, you have to wait for everybody else to go down here. And this is how we're going to use this. Yeah, we're going to use this reader-writer concurrency on top of the B tree and also BP tree. Like it's basically the same schemes that we talked about, but they become a little more complicated. So we talked about optimistic concurrency control a while ago, but to recap what it is, optimistic concurrency control takes advantage of this fact that most modifications to the B plus tree don't require a split or a merge. Almost all of them are just in the leaves. And so the most naive concurrency control in a B tree, like if you just had exclusive lock, you would have to take the exclusive locks like hand over hand, top down. But that causes a lot of contention on the root. And so in optimistic concurrency, you take reader locks all the way down, and reader locks don't cause contention because people can take them, like other threads can take them in read mode also. And almost all the time, you don't have to write to the internal nodes, only one every B elements. So instead of assuming that there's going to be split or a merge, and instead of taking them in exclusive mode, you do this optimistic traversal using reader locks on the way down. And then if you guess wrong, like if you had to do a promotion and you find that when you get to the bottom, then you start again and you take writer locks from top down. This is regular optimistic concurrency control. You can implement it with the reader-writer lock that I just showed you. You just take them in the different modes. You always have, sorry, and you always have to take the right lock on the leaf. In insertions. For range queries, in regular B trees, sorry, I should say read only, but in regular B trees, range operations are read only. So you can just take the locks in read mode always. You just do a find from top down in read mode, and then you read locks left to right for like as many nodes as you need to until you finish your iteration. I think this is the same example that I gave a long time ago, but I'll do it again. Suppose that you have this iterate range. You start at key 25 and you want to iterate 2 elements. You take the read lock at the top. You keep going down to the correct place. Read locks all the way down. And you take this, you get to the leaf and you start at 25, but there is no 25, but this is the correct leaf that it would have been in. And then you do your range query and you step over to the right one, still in read mode. And then you complete this with two elements. And the question is, how do we modify this for range query concurrency in this BP tree? Is it clear that the insert scheme doesn't need to change? Or maybe somebody can tell me why the insert scheme doesn't need to change. Again, like, remember, like this internal array and this outside pointer node structure are independent.
Like there's a, it's exceeds the size, then it has to like change the whole thing, right?
Can you say it again?
So like if an insertion breaks on like overfills one block,
Mhm.
then the whole thing have to be redistributed.
Yes, but the whole thing is still enclosed in one, like you have to take only one lock for this entire array.
Oh, you're taking for the insertion.
Yeah, because when you take like the lock. When you take the lock in the B tree or any B tree variant, it's the lock for the entire node. Whatever data structure you used inside here, it happens to be an array. But like when you replace it with this BPA, it's still for like that blob of memory. Or like, no matter what size the node is in terms of blocks, like every node, every lock still corresponds to one node, no matter what was in the node.
But what if it goes from one node to another?
Like if you have to do a split, then you would have to take right locks left and right. But that is the same as if you had to do a split. In the regular B tree, like think about doing the concurrency control on a split. You take like the thing you have to split and the thing to the right of it, and you have to fix up the pointers. You have to do the same here. Like if the array becomes full, you're gonna have to split it in half, but the node level thing is the same. I know that's not a proof, but it's like the high level idea. Like the concurrency scheme depends only on the B tree structure and like the operations that you have to do on the node level. So I claim that you don't have to change optimistic concurrency for the inserts at all, like because you're still you still take the read locks and the write locks when you need to, but I claim that you may have to change it for the ranges. Yes, exactly. Yeah. So the reason that here this is just in the regular B tree, and you could take read locks always because you're just reading. But in the BP tree, it becomes more complicated because sometimes you have to sort. Yeah, so the problem, the range queries may modify the array because you need to do sorted step through sometimes. And the naive solution is like you take the read locks on the way down because nothing has changed in the internal levels, but then you always take the writer locks on the leaves. And that's not wrong. Like, because if you take it in writer mode, you have exclusive access, and so you can do whatever you need to do, like sorting or otherwise. But the problem is that the performance is actually fine when the distribution is uniform, but the performance is quite poor when the distribution is skewed, because everybody wants to go to the same leaf, but everybody's trying to take it in exclusive mode. Yeah. Okay. There are these issues. You can take the reader locks on the internal nodes, and now you have to, when you do the scan, you have to take them in write mode. And one way that you can solve this, though maybe there are other ways, but this is the way that I happen to do it, is remember that there's a spit vector. So this is not going to save, this optimization doesn't save you in the worst case, but it turns out that it does save you a lot in the average case, even when the distribution is skewed. You only need to take the high level intuition is like you only need to take the write lock when you know that you have to write, and you can use the spit vector to tell when you have to write, because up front you know like the range of your iteration, and using the header you know like which blocks you care about, and so you can take the read lock first. You can check whether the log is sorted and whether or not the relevant blocks are sorted to what you need, and if they're already done, you don't need to take it in write mode. It's already in a perfectly fine state, and you can just proceed with your read lock. Otherwise, then you have to upgrade to a write lock and do your fixing. But only one person has to do it then, until the thing gets rewritten. So that is one way to decrease the contention. So I don't have any proof that this is the best way. So.
But then this would still like if the input distribution is skewed, it would still not help you. Only if it's uniform, then a right read lock would be enough. But then if it's skewed, then every time it's adding, or like every time you're reading, there is a sort, so you still have to like get the right lock.
This helps you also when it's skewed, because first is that oftentimes you're only writing to the log. So even if your input is skewed, you don't often write to the blocks. So like, and then only if somebody sorts it before you and you check it, then the log is already sorted. Like only between insertions to that node, only one person has to sort it. It is less effective in this case, but still works. But you wouldn't need this in the uniform case, because in the uniform case, it's just perfectly distributed. Yeah. Good. So let's talk about the evaluation. This might help because I think a bunch of people are doing data structures projects. So this is one way that you can do the YCSB evaluation. So YCSB stands for Yahoo Cloud Survey Benchmark. And the way it works is that there are two phases in the benchmark. The first one is called load, where you add some base number of elements, and this can be pre-generated, and you don't time this part. Second part is called run. And in run, some workload is defined with some breakdown of operations, and you can also pre-generate those. And you run those operations all concurrently, and this part is timed. And often, though not necessarily, they are equal in size in terms of number of operations. And there's also a question of distribution, but distribution is like an orthogonal question to both the operation distribution and this like load run setup. So for concreteness in this evaluation, each phase happens to have 100 million operations, and you can also define some distribution like orthogonal to the workload distribution and orthogonal to this breakdown. Oh, shoot. Sorry. This is just the machine specifications. This is one machine. It's 48 cores, it's two-way hyper-threaded. This is the CPU, it runs at 3 gigahertz. This is the cache parameters, some L1, L2, L3 size. And it's not reasonably big, it has almost 200 gigs of memory. So this B tree is in memory, and all experiments are run on a single socket using half the physical cores and half the hyperthreads. And this is like a regular way you take the median of 5 trials. So, this is just an example of like what one of these evaluations looks like. But yours doesn't have to be like exactly this big or this deep. It's just like this is what it looks like. So the way that YCSB works is that they give you some default workload configurations, and the operations, like I said, there's like find, insert, and then there's range query. And the default one is short range with average size 50. And they give you these generators to define these workloads. And then this is like 50-50, find and insert, 95-5, find and insert, 100% find, and 95-5 short range and insert. And they have letters. I think this is like A, B, C, D in YCSB. D is like find min or something, so we skip that. And YCSB allowed you to generate these OLTP workloads, and we also generated these OLAP workloads by ourselves, long range iteration and long range map. I think long was like 10,000 or so, average length 10,000 maybe, max length, I don't remember. And these are just to exhibit like the long range queries that I'm talking about, but because YCSB is not designed for OLAP, like they don't come with this. But you can generate these in YCSB, you just change the parameters in the workload files. Yeah, and then we did this comparison with these other things on the market, mass tree, OpenBW tree. And the way to read this is normalized performance. 1 is BP tree, up is good. And this B plus tree is something, it's just like a base implementation. It's just I think people are maybe doing this, so maybe yours is faster than mine. This is just like a regular weekend project. This is a B plus tree with optimistic concurrency control, like bolted on top of it. It's from TLX, which is like an open source B plus tree. So yeah, so 1 is good, or like 1 is default. BP tree higher means that it is better. So here, like the purple bar is slightly faster than BP tree because this thing is optimized for point operations. So it's slightly faster. The other ones are slightly slower, but you can see that it suffers when you get to range queries. This purple bar here is 0.14. Later on, it becomes 0.03.
Performance was measured only on the find operations, or is it on insert and find?
It's on, so this is like the run phase.
Right.
So it's like, in this case, it's measured, you have like a set of operations, 50, 55 insert, and you do like a parallel for over the set and you measure how much time it takes you to finish.
Just like you mentioned that, we don't measure the load operations. I thought load meant insert. You know,
Load is insert, but you can also perform inserts in run.
what's the need for load then? Like,
Load is just to make sure that the data structure is not empty
uh,
in the start of time. Just to make sure that you have some stuff in it already. Because if like, for example, like 100% bind, if there's nothing in there, it doesn't become very interesting, so. Yeah, good question. Yeah, it's a little confusing, yeah. Yeah, it is a little weird that like you can define insert both in load and run, but insert is only timed in run. So you could also like I've seen some papers, they report the load time, but just like the overall load time. But I think run is always reported and load is sometimes reported. I've seen. Yeah. So to recap the results from the Gitmo, like I said, BP-tree matches the performance of the point operations and improves the range queries by 1.5x at best, compared to just this off-the-shelf B-tree that we put optimistic control on. It turns out that the other research level things are quite poor in range query down there.
This data set have another data, so now we can see it has the composition of the operations we work, but I think there's another dimension called the concurrency. For example, how many concurrent threads we have to perform these operations.
Yes, the threads is determined by the machine, I guess like the scheduler and the machine parameters. It's just like we put like parallel, you have a set of operations, like 100 million operations, and the data structure is thread safe, and you just put parallel for 1 up to n, where n is the number of operations you have, and then you perform that operation.
Oh, so it's determined by machine.
Yes, yeah. Like the number, as long as the underlying data structure is thread safe, it should be fine to just rely on like the machine scheduler. Mhm. Good. Good stuff. Okay, yeah, so this is, like I said, this is some other small micro benchmarks. This is insert and find. And then dotted line is the B-tree. Solid line is B-tree. X-axis is leaf size, y-axis is throughput of BizBin. And you can see that at the best configuration for B plus tree, it is better. It is similar to the best configuration for B-tree. Yeah, this I feel like these analyses are kind of weird because like the configurations are not necessarily the same in all comparison points, but you're kind of comparing like the best configuration of one to the best configuration of another. The main thing to note from this is that as the leaf size grows, these dotted lines degrade more gracefully. And these are kind of falling off. And this is what, I forgot who was saying it, but if you do the same experiment for range scans, indeed, there is a lot more computational overhead as the scan grows in size. Like if you fix the leaf size, yes, definitely the B-tree scan is better than the BP-tree scan. But the point is that you can't fix the range size, or you can't fix the node size of B-tree without paying in the without paying in the insert. And like the computational overhead is smaller in the short scan, which makes sense because you scan over fewer nodes. Questions? Okay. Yeah, so in the last part, I want to talk a little bit about performance modeling, which is hard, but I'll talk about it a little bit. So this is going back to what we had in the very beginning. This is normalized performance. This is node size in bytes. And traditionally, node sizes are small. Like if you look at the default TLX distribution, their node size is 256 bytes. TLX is like a B-tree, it's a serial B-tree. And however, you can see that the range query is continuing to improve when the nodes are getting way bigger. This max size is 64 KB, it's pretty big. And one way to model that, though not perfectly, is we talked about caching models a while ago. In caching models, you have these two levels of memory. You have small memory and you have big memory, and you transfer data in blocks between them. And one block transfer has 1 unit cost in this model. And so in the DAM, which is the most, the disk access model, which is the most simple caching model, every block has one unit cost, no matter where it is in the memory, whether it's contiguous or not contiguous. And so here you transfer 5 blocks and the total cost would be 5. However, there are more refined models, like the affine model, that accounts for the relative cost of sequential access versus random access. And sequential access is faster because there are things like prefetching. And yeah, so in this model, it's also relatively simple. Random access has unit cost and sequential access has cost alpha much less than 1. And this is originally designed for disks and accounted for disk seed cost versus disk read cost. And in this model, like the same workload would cost you 3 plus 2 alpha, where alpha is less than 1 because these 2 blocks are contiguous after that one. So you have to pay 1 for like the first one, and you have to pay 2 for the later ones. And the goal of this is that we're going to try to use this model to explain what we saw, because in DAM, like everything is the same cost, because as long as you read one cache line, everything is optimal from there. But of course, like as we just saw in the performance numbers, not everything is the same. And so we're going to try to do some, like try to map this onto empirical measurement. Okay, so there are 2 main parts in actually filling in the parameters. The first one is that we want to find alpha. Let me go back. You want to find alpha, and you also want to find R, which is like the cost of block read. So the way that we find alpha is something called scan test. And the way that scan test works is that first you allocate, the high level intuition is like we're trying to find how much does it cost to read random blocks versus how much does it cost to read contiguous blocks in like empirical numbers. And the way that we're going to do that is first we allocate this giant array of X bytes, like something like gigabytes. And we're going to iterate through block sizes from 1 up to X in powers of 2. And then in parallel and in random order, we're going to scan over the entire array and separate blocks of size B, where, sorry, this should say L. Blocks of size L, because L is here. And yeah, so you have this giant array X size, and then you cut it up into chunks, like you measure like a for loop, L from 1 up to X in powers of 2. And then for every L, you cut up your X into these chunks. And then you, with multi-threading, you just shuffle the order of them and you read them in parallel. You read a disjoint set of them in parallel. So every experiment, no matter what, so what you want to do is like every experiment, no matter what L is, you're reading the same number of bytes, but you're reading a different amount of them in order. And like I said, you also need to find R, which is the cost of reading a random cache line in DRAM. And the way that you can do that is you just set L equal to Z, which is the cache line size. And you know the cache line size is usually 64 bytes. And then you compute this latency of reading the cache line in DRAM, because you have the total time that you took to read the entire array, that's the measurement, and you have the total number of lines read, that's just X divided by 64. And so if you divide those, then you can get the time per line. And using that thing, we derive these parameters. Alpha on the machine was 0.3, and R is like almost 2 nanoseconds. And this machine has a cache line of Z equals 64 bytes, and we can use this heuristic of write cost. Sometimes you also need to measure the write cost when doing this performance measurement or performance modeling. We use this heuristic that writes about 2x as expensive as reads. And if you have some expression for your cost in terms of these parameters, and you have these empirical findings for your parameter values, then ideally you can get this predicted time for the operations. In reality, when you try to do this, it's actually really complicated. And like for example, if you want to come up with an expression for the cost of like this BP array insert, like it depends on like the distribution, it depends on like what insertion you're doing and stuff like that. So this thing is actually not as nice as it looks, but that's kind of how you would do it. Yeah. Though I don't want to talk about how exactly to do that because it's kind of ugly. So, but we can do this nicer thing, which is how do you do this measurement using the scan test? This thing is way easier to talk about. This is the relative time to scan 8 gigabytes, which is X in this case. 1 is the slowest, down is good. And this is the block size in bytes. So this is how you set L. And in the DEM model, it doesn't matter what your block size is. This is just how much time it would take you to scan this entire 8 gigabytes, and it's fixed. But of course, as you can see, this empirical line is going down because the bigger you make your block, the faster it is to, the more data you read contiguously, the faster it is to read the data. And the red line is the time predicted by the affine model using the user set parameters. And it is easier to set, it's easier to make the expression for such a simple operation. One weird thing that I want to point out is here, this 3.1, this is like speed up over the worst thing, or sorry, speed up over one cache line actually. So 1.0 is the normalized thing where block size is equal to 64 bytes. And one cache line, or sorry, this thing is 3.1, which is 3.1 times faster than when L equals to Z. But this is one page size and it actually gets better after one page size, which is a little weird because in the Intel model, in the Intel manual, they tell you that the prefetcher doesn't cross page boundaries. So prefetching cannot explain why this is getting better. Yeah, so like I said, the Intel manual tells you that the prefetcher goes up to page boundaries only and pages are 4K in size. So why is it better after 4K? To try to understand why, we did extra benchmarking. There's this Intel Performance Scanner monitor that you can measure additional metrics, like you can measure L3 cache misses, which is a normal one. A weird one is you can measure bytes read by the memory controller. And this is the block size. This is the y-axis distance from best. Down is good. And extra bytes read means that like you have the minimal number of blocks that you needed, minimal number of bytes that you needed to read is the size of the array. But the memory controller may read more depending on what your block size was. And actually you can see that like this pink line is often above 1. And the reason for that is in some cases because the page size reads or like, oh yeah, because of page reading or cache lines or whatever it is. And even after page reads, even after page read size, the pink line is still above 1. And there are extra bytes read by the DRAM memory controller still after that. So that is the conjecture about why it's still getting better and this pink line is still going down. To wrap up, B-trees and any other block data structure like B-skip lists would also exhibit this trade-off between point and range operations depending on the node size. And the affine model provides a way to analytically determine the benefits of these larger node sizes during the scans. And BP-tree overcomes this decades-old point range trade-off in B-trees. It can increase the performance for their workloads that include both point operations and long scans. And I want to say that based on this point, this trick of like replacing what is in here doesn't have to be an array. Like if you want to experiment, you can just replace it with like a hash table or linked list as you said, and then you would get somewhere else on the trade-off. And this trick of like replacing the internal thing does not apply just to trees. Like you could apply it to skip lists, for example, or anything else. Yeah, that's all I had for today, but I'll take questions if there are any. Yes, so let me go back. Could you just copy it and sort the copy? You can, and actually that in range map, that is actually what we only copy the log because it is expensive to copy the entire thing. Actually, we did try copying the entire thing, but because these things get up to like more than 1K size, it is expensive to copy the 1K every time. So that is why in the range iteration, especially in the short range iterations. I see. So you're saying like we had to iterate this entire thing. Copying is order n, and then the sort is log n. You need to copy the blocks also. Like if you're doing full sorted iteration, both the log and the blocks need to be sorted. if you're just doing map, like, not map, like, if your API is just like between elements, key X and Y, then you can just copy this thing. And then this thing you can iterate in any order within the range. But indeed, like, it is not incorrect for both cases to copy this entire thing and just sort that, but it is expensive, especially when the size of your scan is smaller than the size of this thing.
A prime queue, and that's a open operation, and then we can just do the range. So that will, instead of another, just.
Where K is like the size of the range. Yeah, it's a good point. Like, I didn't do much experimentation, like, because the scheme needs to work for arbitrary scan sizes. And so anything that involves copying the entire thing doesn't work so well when you're like, you have to account for both you cannot pay in short scan for a long scan. Because then like that's one of the default workloads, so you have to maintain performance in there. So anything that involves copying the entire thing or building like a data structure of the entire thing, you cannot maintain the short scan performance. But if you only cared about long scan, I agree, like there might be faster things, like just copying and sorting might be better. Yeah, super. Thank you. Cool. Thank you.